Our first step should be to create a local coordination system that is attached to this geometry and moves with it. Okay, let's display point numbers to help us build a coordination system. Create an import point attribute. Connect the geometry to it. I'm going to import the position of point 24. Okay, let's call this point 24. Now let's duplicate these two nodes. Rename it to point 10. Then specify point number 10. Let's make a copy again. Rename point 25. Then specify point number 25. That's all. Now we can build a coordination system based on these three positions. Let's create a subtract node. Then subtract point 24 from point 10. Okay, now we get a vector directed from point 24 to point 10. Let's normalize this vector, then export it as a y-axis. Specify the type as a vector, then call it y-axis. Let's give it a green color. Now copy this subtract node. Connect the point 25 to the first input just to get a vector directed from point 24 to point 25. Let's normalize again this vector. Then export it as an x-axis. Let's make it red. I will swap these two nodes just to have a correct order. Excellent, now we can generate the z-axis based on these two vectors. Let's create a cross-product node. Connect these two vectors to it. Then export it as a z-axis. Let's make it blue. Here we go, now we have a coordination system. Now let's organize these nodes, select all this, then create a subnet. That's it, now I want to visualize these three axes and see what it looks like. Let's right-click on this icon. Then click on the plus, select marker. Let's call it an x-axis. Specify as a vector. Select a point. Then choose an x-axis from here. Let's color it red. That's it, we visualized the x-axis. Now let's do the same for y and z-axis. Take a look, now we see all three axes. The only thing I want to change is to invert the z-axis. For that we just need to swap the cross-product inputs. Let's get to it and fix it. Select the cross product and press Ctrl-R. That's all, we reverse the z-axis. Okay, now we have a local coordination system. It means we can extract the transformation matrix relative to it. Let's disable the visualization of vectors. Then click on this to expand the network view. Then press P to bring up the parameters window. Okay, now let's extract the rotation matrix from this animated tube. For that we need a vector to matrix 3 node. This operator converts row vector values to a 3 by 3 matrix value. We must in turn connect these three vectors to it. Now let's export this rotation matrix. I will call it rotate matrix. The type must be matrix 3. Now we can try to rotate another geometry by using this rotation matrix. Let's check the newly created attribute. Here it is. Now let's create a box. Then create a one more attribute VOP. Connect the box to the first input. The animated geometry to the second input. Then dive inside. Now let's import the rotation matrix from an animated object. Connect the second geometry to it. The point number can be any point of tube because a rotate matrix attribute exists on each of them. Specify the type of attribute we are going to import, then enter the name of the attribute. That's it, we import the rotation matrix. Now let's use it to rotate the box. We have to multiply the position vector by this matrix. Now let's check what we get. Here we go, the box perfectly repeats all the rotations of the animated tube. In order to repeat the movement of the tube, we have to extract a full transformation matrix. Okay, let's go on. Now I want to exclude rotation from animation using inverse rotation matrix. For that we need to multiply the position by the inverse rotation matrix. Now we need to invert the rotation matrix. This operator computes its inverse. Okay, let's check what we get. As you can see, we exclude the rotation, the tube only moves. Okay, let's move on, we can delete these two nodes. Now I want to extract the full transformation matrix. For that we need a vector 4 to matrix. This operator converts row vector values to a 4x4 matrix value. As you can see, this node takes only vector 4, but if you connect a regular vector to it, the Houdini will automatically convert it to vector 4. But still I'm going to convert. Let's create a vector to vector 4. Then convert the regular vector to vector 4 and connect to the first input. Okay, now let's convert the rest two axes. Then connect to the vector 4 inputs, in turn. That's it, we only need to set the fourth input, which should be a position vector. Let's create an import point attribute. Connect the geometry to it. Look, I'm going to import the position of point 24. Let's create a constant, then put a 24. Now we need convert the regular position vector to vector 4, then connect to the fourth input. For the position vector we have to make a 1 the fourth component. That's all, we have extracted a full transformation matrix. Now I'm going to export it, then use it to move the box. Let's call it a full transformation matrix. Specify the type. Great, now let's use this to drive a box. Duplicate the import point attribute. Enter the name. Then specify the type. Okay, now let's disconnect the rotation matrix, then connect the full transformation matrix. That's it, let's check what we get. As you can see, now the box repeats not only the rotation of the animation object, but also the movement. The box is attached to the point number 24. If we change the point number, then the attachment location also changes. Let's check out. That's it, the box sticks to the point from which we take the position. Now I want to show you how you can stop the animation and bring the geometry back to the origin using the full transformation matrix. For that we just need to multiply the position vector by the inverse transformation matrix. As you noticed, the point from which we take the position has moved to the origin. In this case it is point 24. Now let's display the point numbers and check. That's it. Now let's change the point number and see what happens. As you can see, the specified point goes to the origin, since the transformation matrix is built based on it. Now let's move the time slider and see what happened to the animation. As you noticed, the torus is not moving because the inverse transform matrix compensates for the existing animations. Okay, let's go on, we can delete these two nodes. Now I want to show you one more important thing related to this kind of manipulation. Let's increase the radius of this tube. Something like that. Delete the box, then create a torus. Let's scale down the torus, then reposition it. Something like that. Okay, now let's connect to the attribute VOP to move with the animated tube. Look, the torus has changed its original position, which is undesirable. Now I want to improve our setup and get rid of this unwanted shift. The reason for this shift is the offset of the point from the origin, on the basis of which the transformation matrix was built. It turns out if we change the point number, on the basis of which we extract the transformation matrix, then the offset will also change. Here we go, the reason for the offset is determined, now let's solve the problem. Okay, let's jump to the object level. Then connect the static tube to the second input. Let's make sure that the second input has no animation. As you can see, the tube is not moving. Let's dive into the attribute VOP. Now let's copy all this network. Then delete extra nodes which we don't need. Let's arrange this network a bit. Okay, now we need to specify the second geometry, which is a static tube. We also need to pick the same point for both geometries. Let's delete this one. Now let's rename the full transformation matrix of the static tube. I will call it offset from origin. Okay, let's use this matrix to get rid of the shift. Here is a newly created matrix. Excellent, let's jump inside the second attribute VOP. Delete the rotation matrix, we don't need it anymore. Let's duplicate this node, then import offset from origin attribute. Create one more multiply node. Then multiply the position vector by the inverse of this matrix. Here we go, the torus returned to its initial position, we compensated the shift. Now let's check if the torus is attached to the animated object. Here we go, the torus moves with the animated object. Look, now we can move the torus where we want, and it will be attached to the animation object. We can even change the point number from which we built the transformation matrix. Take a look, we have no shift. Okay, let's move on. The last thing I want to show you is how to exclude the translation and keep only rotation from the full transformation matrix. For this there is a special node called orient. This operator reorients a vector representing a direction by multiplying it by a 4x4 transform matrix. The translations associated with the 4x4 matrix will be ignored. Okay, now let's connect the position vector to it. Then multiply it by the transformation matrix. Connect the output vector to P. Now let's check what we got. As you can see, the torus doesn't follow the tube when we transform it. But as we start to rotate it will follow. Here we go, we keep the rotation but exclude the transformation. That's all, this concludes whole lesson. I hope it was useful for you. I did my best. See you in the next lesson.